Yeah, so thank you for coming a second time. I'm sorry I missed it the first time. Right, so this is going to be about a consensus method for finding a consensus tree. And this was just supposed to be, there was maybe too many word plays here, but yeah, something about genes and also we'll introduce the program RTIST, which stands for rooted triple, gosh, I forgot, tree. James came up with the name. Anyway, let's begin. So I'll give a quick overview of triplet quartet-based consensus methods. So particularly Astral is the big one. Then I'll give construction for the triplet median tree bottom up using a little bit of clustering, which saves some time. And then I'll compare the result with what exists currently. And so this is how it works. So triplet and quartet-based consensus methods basically deal with this problem. We now have high-speed DNA sequencing, which makes accessing an abundance of gene trees very practical. At the same time, under the multi-species coalescent model, the most probable gene tree may differ from the species tree. And these are the so-called anomalous gene trees. It's not always a given that that will happen, but you kind of don't know which parameter regime you're in. And if you happen to be in the wrong one, that can happen. So the problem is non-trivial, but you can get around it by looking, instead of looking at the most probable gene tree, looking at the median tree with respect to a different distance. So generally, you can define the median tree of a set of trees with respect to some distance function d like this. You just take the tree which minimizes the sum of the distances to every gene tree. And you say, okay, this is my median tree. And hopefully if you can come up with the right distance, you can get around whatever problem you have. One of the very popular ones are the triplet and quartet distances. Quartets are probably much more popular because of Astral, but the approach is essentially the same. And they're based on the observation that anomalous gene trees are impossible in the case of a rooted phylogeny with 3 taxa or an unrooted phylogeny with 4 taxa. And so that motivates the quartet and triplet distances, which just count the number of quartets or triplets on one tree, but not the other. And with that distance, you can define a median tree with respect to these distances. And it turns out that that's a consistent estimator of the species tree under the MSC. So this observation is the basis for many popular methods, possibly all of these as one method, you could say. So Astral, Astral 2, and Astral 3 are very popular, Astral and P as well. They all use the quartet distance. And Stellar is based on the Astral 3 code base, as far as I understand, and that's based on triplets. So you just count triplets instead of quartets. The way that they all work basically reduces to the following question. You start off with a set of all your taxon labels, and then you split it up into a bipartition. So this is a disjoint union. And then each one of these you split up into another disjoint union, and so on and so forth until you have your tree fully resolved. And so implicitly throughout this whole talk, I'm going to be talking about just binary trees. So nothing missing or trifurcations or anything like that. So this is the broad idea. And to do it, we need to compute the number of common triplets between a candidate phylogeny and the inputted gene trees. So Astral uses quartets, so the formulas are going to be a little bit different, but I'm just going to focus on triplets because that is what I ended up working with. But the derivations are essentially the same. So we can do it in a few steps. The first one is to actually just find an identification between the triplets in a tree and some kind of a common, some kind of a node inside the tree. So over here, you can see that a rooted triplet always maps uniquely to the most recent common ancestor. So U on this picture, or equivalently, the subtree bipartition corresponding to that common ancestor. So for instance, if you took ACD, so if you took this guy and these two guys, you get this triplet right here, and they uniquely map to U. But it's obviously not a one-to-one map. There's not enough nodes, so it's kind of a many-to-one map. But you can count them very easily. Well, you can count the number of triplets that correspond to a specific node very easily. You choose one from one side, then you choose two from the other side, and then you do it the other way, and so you get this very simple formula. So in this case, you get 9 triplets, which is exactly what we get when we count them one by one. Right. So that's a mapping to a node, and that's the first step to computing these distances. The next step in doing that is counting the common triplets between, let's say, between two trees. So you can view that as, you can reduce that problem to a simpler one and ask, okay, if I have a subtree bipartition, meaning just the bipartition of the tree, below this this node. If I have two bipartitions, how many triplets are there that that belong to this bipartition and this bipartition? And the calculation is exactly the same. You basically say, all right, I want to make sure that the outgroup is is here and here, and then I have a pair in the other part of the bipartition, and you run this argument 3 more times, and you get this very nice formula, which really is just like a quadratic polynomial in the magnitudes of the intersections. And once you have that, you can sum over every node in one tree and the other tree to get the total number of common triplets between both trees. And so again, this gives you the number of common triplets between two trees once you do the summation, but that's not a very useful thing if you just have one gene tree, right? You could have just done it manually. But it's very useful for talking about the distance from candidate phylogeny to a set of gene trees. So in the presence of a set of gene trees, this curly T, the number of gene tree triplets corresponding to a candidate phylogeny is subtree bipartition AB. So this would correspond to a subtree bipartition split. Would just be this number, right? You would fix A and B, the subtree bipartition and the candidate phylogeny, and then you just iterate over all the subtree bipartitions in all of the gene trees. So you get this double summation. So you're summing over the nodes inside a tree and over the trees inside the set of gene trees, and that'll give you the total number of gene trees corresponding to AB. And we call this the weight of the pair of disjoint sets AB. The reason we define it is the following. Eventually, what we want to do is we want to get the median triplet tree or the median quartet tree, and that would correspond to, well, to do that, you'd have to at some point calculate the total number of common triplets or common quartets with the gene trees. So you could define it like this. You could say C is the total count of common triplets with the gene trees, and if you we define C of L recursively like this. You put in the set of taxon labels, and you say that has to be the maximum of the value of the same function evaluated over at a subset of L, and the complement of that set, plus the weight of this bipartition that I've created, right? So presumably there is a best bipartition if you're subtree bipartition if you're computing the median subtree. And so that would have to be E and L minus E. If your set is has size 2 or 1, then the count is obviously 0. You can't fit any triplets in there. And then there is a very reasonable interpretation of this, and it's that this term over here is just the number of triplets which map to the top of the median tree on this set of taxon labels. And it doesn't have to be all the labels, right? It could be a subset. And then the first two terms is the number of triplets that map to the other nodes. So, right. So that's how you can interpret this equation. So how to solve this? So to compute it, you pre-compute the, broadly speaking, you pre-compute the weight of AB for all possible pairs. So the quartet or the triplet count. And then you compute C of L recursively. So in a top-down sense when you're solving dynamic programming problems. And then you find the median tree by backtracking through the computation. So it's basically like computing the Fibonacci sequence. And rather than recording the values of the Fibonacci sequence first, you say, well, f sub n is equal to f sub n minus 1 plus f sub n minus 2, and then you have this bifurcating diagram. And this is what Astral and Stellar do. So in this talk, we'll do something a bit different. So rather than do that, we'll compute C of L bottom up and pre-compute the weights just a little bit faster. Okay, so let's see how to do that. So the naive approach to doing that would look like this. You iterate over every gene tree subtree bipartition. Then for each bipartition, you iterate over all possible disjoint pairs of label sets which intersect with the bipartition and increment the corresponding element in the weights array. So broadly, it looks like this. You have your gene tree, then you say, okay, A and B is some set. So now that I have my gene tree number 2, I'm going to find the intersection of this set and this set with A and with B, and I'll do that a bunch of times. So I'll do that for every gene tree and for every A and B. Obviously, that'll be a nightmare to compute, especially as your number of gene trees increases. So we wanted to speed up this process. So obviously, you can't get around the fact that the number of necessary computations grows super fast, but you can at least reduce it. And hopefully these ideas are also useful in the approximate case. And actually, I guess I neglected to mention this at the beginning, so maybe I'll take the opportunity to say it now. The reason that we're working on this project is James and I were interested in the differences between the quartet and the triplet distances, and how good of an estimator the median trees with respect to those distances are. So we wanted to perform exact calculations, not the approximate ones that you might get with Astral. And so this is kind of an algorithm suited for that purpose. So it's an exact calculation that can handle many, many gene trees, because that's what we were interested in. Okay, so to do that, what we're going to do is we're going to speed up this algorithm in two ways. The first one is we're going to group identical subtree bipartitions from different gene trees together and do the necessary calculations just once. So that makes a lot of sense. If for instance, if for instance we had a bigger gene tree, if there is another gene tree that has this as a subtree, then it doesn't really make sense to run all the calculations twice, right? Once you've done the calculations once, that's enough. You can maybe cache it somewhere and then plug it into your array over and over again. But somehow even that's not enough. So the other thing that we'll do is group the gene tree subpartitions. Group the gene tree subtree bipartitions, which require updates to the same elements of the weights array together, and reduce the computations there too. So the issue with pre-computing these weights arrays is that there is a ton of elements you have to update. Updating things in memory is not instant. You have to access it. The arrays are quite large. You have to access them quite far, and so all of that combined makes things very slow. So we want to get rid of that effect, or minimize it anyway. So so here's the first version of this algorithm. So suppose that you have this bipartition XY, which occurs in some number of the gene trees, like I was saying, and let's call that M, like a count. So triplets corresponding to the most recent common ancestor of X and Y contribute to the weight WAB only if you can write A as this disjoint union of something kind of like a kernel and something in the kernel and something in the co-kernel, I guess. So if you write A as a union of A prime and K1 and B as B prime union K2, where A prime and B prime are disjoint and not empty and are subsets of X union Y, and K1, K2 are subsets of the complement of X union Y, and they're disjoint, then any set of this form, any pair of sets of this form, is going to contribute to WAB. The reason being that if I'm going to scroll back for a moment. So we're writing A as a piece that's inside X union Y and a piece that's inside the complement of X union Y. So I'm going to scroll back for just a moment. Over here. If you plug that into here, you immediately see that, because you have to compute these intersections, those kernel bits just fade away. They really don't matter when you're doing the count. And so we can briefly say that the contribution to the weight is independent of the kernel and simply equals to the count that you would compute for any one of the chosen bipartitions, multiplied by the count of XY. Right. And so if you wanted to implement it on a computer, it would look something like this. So you have the set curly B of all gene trees subtree bipartitions. You iterate over all the gene tree subtree bipartitions, and for each bipartition, you find the kernel and iterate over all pairs of disjoint subsets, and you increment the weights along the way. So it's kind of a mouthful, so I thought I'd include some algorithms to really to make it clear. So the idea is this: X and Y are the subtree bipartitions that you have in the gene trees. There is, not too many of them, just, some scalar multiple of the number of gene trees you have inputted. Then for every disjoint subsets A prime and B prime of the union of X and Y, you calculate the number of triplets that are in common with xy, and then you multiply it by the number of times that xy occurs as a subtree bipartition. Then for, since you know you don't have to do this computation anymore, you then look at the complement of x union y. You look at every possible pair of disjoint subsets, and you update the weight for A prime union K1 and B prime union K2 by this delta that you've computed over here. And then you end the loop, and you have to run it many times. That is how you do it. I should say that a lot of these calculations are very easy. Traditionally, they're done with bit set representation. I didn't include it in the slides, but we worked out how to do this in base 3. It made it compressed the data by a lot more. So there is an effective way of storing this. If you store it as binary bit sets, then kind of takes up too much space. Right. So that's how you do that. The important thing to notice here is the following. A giant part of the calculation comes over here, because you're looking at all the subsets, all the pairs of subsets, I should say, the disjoint pairs of subsets of this L minus X union Y. But if you look at it long enough, you realize that it doesn't really matter what X and Y are. It only matters what the union is. And so if you somehow pre-computed the sum first and then looked at and only then did this inner loop, you would save a lot of time. And this is exactly what we ended up doing after kind of fighting with it for a long time. But before I show the algorithm, let me maybe show the motivation for this. If you generate some species trees as a pure birth process with 16 taxa, and then you generate some number of gene trees, so let's say 200,000, 400,000, whatever. Depending on the birth rate, you can expect to have this. At some point, you expect to have the saturation of the ratio of bipartitions per subset, meaning you have like a cluster in your data in your gene trees, and then you look at the total number of bipartitions in your data, and you just you look at the ratio. You'll find that well, obviously the lower your birth rate is, the faster it takes to saturate, but it does saturate eventually, right? Even here, you can kind of tell that it's starting to saturate a bit. So the idea is that by combining the calculations here, we can take advantage of this saturation and then say, okay, it's going to take me a lot of calculations to do the first 200,000 gene trees, but the rest are going to be pretty cheap. It's not really going to add much for me. And this is how you end up with this. This is the modified algorithm that you end up with. So you let C be the set of all the clusters in the gene trees, and you let curly B be all the subtree bipartitions in the gene trees whose union is equal to U. So all the ways that you can write U as a union of a union of the subtree bipartitions in your data. You can pre-compute this pretty easily. And then you have this algorithm, which I will soon show you is a little bit faster. So you zero initialize a weights array. For every cluster now, you do the following. You find disjoint subsets A prime and B prime of U. you initialize this delta to count the number of gene tree contributions, triplet contributions. And then for every gene tree subtree bipartition, you figure out the contribution to this delta. And over here, we're not talking about the kernel quite yet. We're basically saying these are going to be all the contributions, and this contribution is now going to be identical no matter what K1 and K2 you choose from your kernel. And once you've done that, you do the second part. You look at all the disjoint subsets K1 and K2 of the complement of U. And you iterate over this thing just once. And when you're doing an exact calculation, this is gigantic, right? If you're like if you have 10 species or 10 taxa in your not corresponding to you, then this is 3 to the 10th, right? So that's already an expensive calculation, and reducing the calculations here creates a really great effect. And you can kind of work out what that would be. So like I was saying, a set U has 3 to the cardinality of U ordered pairs of disjoint subsets. So for the the algorithm that I gave you, the operation count looks like this. It's not really that important how you figure it out. You just you sum over your clusters, then you have to sum over this B. You can get a very rough bound by saying that that the sum over all the bipartitions corresponding to U summed over U is this thing. So this is the bound they use in Astral when they're trying to figure out the complexity of Astral in its approximate mode. But we can also use it to bound the number of clusters that we have given the number of bipartitions. We can bound the sum of all the bipartitions we have as a power of the number of clusters that we have, but this is a very rough bound. And improving it is a little bit hard because like the co-author on this bound is Terence Tao, so I can't do much better than that as far as my abilities go. But the thing to notice here, though, is that usually don't include something like this in a calculation like this, but I wanted to highlight the fact that the number of operations here depends on the number of clusters that you have. Whereas for Astral, the number of operations depends on the number of bipartitions that you have. And so in that graph that I showed you where everything saturates, this is exactly what's causing the speedup that you'll see over Astral to occur. Additionally, I haven't really gotten there yet, but this is a very easily this is a method that's very easy to parallelize. It's a little bit harder to do with the standard algorithm that Astral uses in its multiprocessing variant, where actually the number of operations linearly increases with the number of gene trees and with the number of, well, I mean, this bit's not really important. But you're not going to have this effect. Like you really just care about the number of clusters. So it's a reasonable speedup, and we'll see that in a second once we actually implement the solution. So the solution now is very easy. Again, the idea was that we needed to count the number of triplets on the median tree. And we just started off with this expression and we attempted to maximize it. And then what we want to do is just backtrack. Well, in this case, once you've pre-computed this W array very quickly, you can solve it very easily. So you you know that C of L for L with magnitude 1 or 2 is equal to 0. If the cardinality of your set is equal to 3, then you have a very special case. This is going to be 0. This is going to be 0. And so you're looking at over all the subsets of E, but this function is symmetric in its arguments, and there's really just 3 choices, right? You just choose the outgroup. And so C of 3 is equal to the maximum over just over the weights that you've pre-computed, where you just stick in a singleton set in the second slot or the third or whatever. Once you've done that and you recorded it, you can go up to to 4 taxa and then to 5 and so on and so forth until you reach the number of taxa that you have, and then you're done. You just backtrack, and now you've obtained your solution. And this is a very simple thing to implement. And what's one thing that's very nice about it is that it is super easy to parallelize. So you really just have to sync up your the C array just once. Every time you go from every time you increase the cardinality of your set by 1. And so in the implementation that we have, we actually using GNU parallel and just passing some files back and forth, you can do this calculation in a distributed fashion, or you can record it and finish the calculation later. It's very simple. It really simplifies a lot of the headaches implementing these sorts of calculations. That's how it works. And so this is the algorithm. So like I was saying, you pre-compute the weights array like we just talked about. You zero initialize the C array, and then for every set of 3 taxa labels, you just you perform 3 lookups and you find the maximum. You stick it in, and you're done. Once you've done that, you can do this iteratively. So you choose your, you look at all the sets of a fixed size, you compute this, you record the value. This is only using values of E of smaller cardinality, and so you already have all those values, and so it's very easy to do. And one nice effect of doing this is that once you have it, you're also able to obtain all the median trees and also even the suboptimal trees. There's kind of this implicit assumption that whenever you run a program, like some consensus tree program, that the thing that you get is correct. But usually there is something there where you need to break ties, and you'll often choose one side or the other randomly. You don't have to do that here because you've pre-computed everything. And I'll show you an example of that. Although it is true that usually you're going to have, if you have many gene trees, your maximizer is going to be unique. Right, so now that we've done it, let's look at a comparison with other methods. So Stellar is the piece of software that is closest to this code. And it's based on the Astral3 code base, but it uses triplets instead of quartets. And like I was saying, we only implemented the exact algorithm. We didn't try to, like compete with these methods. We just wanted, we had our purposes of many small trees. But nevertheless, if you look here at the number of gene trees and you look at the runtime, you see that, well, this should say RTIST. Right, that's a new name. You see that the runtime is much smaller, and it's much smaller for both the exact calculation and the approximate calculation, which really surprised me. I thought that, I didn't think this would be competitive with the approximate versions, but it was, to the point where actually, I had the simulations cut out, after a certain time, and we were able to get many more gene trees with this exact algorithm than we could with the approximate version of Stellar. But I should say that Stellar is single-threaded, so maybe that had some, well, certainly that had something to do with it, whereas mtrip is, or RTIST is not. So in some sense, then Astral MP would be the better comparison because it's multi-threaded. And here the exact same thing happened. So again, 16 taxa, different birth rates. You can see here that that even the approximate version of Astral is a little bit slower when you get to a big number of gene trees. And what happened over here is around the 500,000 gene tree mark, which I know is becoming quite unreasonable. Astral would either time out or it would actually run out of memory. And just out of curiosity, we tried, we assumed that the time complexity would be something like number of gene trees to the power alpha. So if you just do ordinary linear regression on the mean for a fixed number of gene trees, you get powers that are a little bit higher for Astral. And they're usually a bit lower for RTIST, although it's worth noting that as the level of ILS is increased, these powers actually start getting closer and closer, which is not surprising because the saturation of the clusters and bipartitions happens a bit later. When we submitted this for publication, we found out something that I personally didn't, I guess I didn't understand, but I now know. And it's that Astral 3 actually uses a polytree structure to not repeat computations. And so in some sense, it attempts to do a similar thing to overcome these complexities. So so we decided we'd benchmark it against Astral 3 as well. And you can see here, this is for lambda equals to 1. You can see here that RTIST is still has better complexity. I guess I didn't record it on the slides, but it's not quite as dramatic, right? I mean, just in the eyeball metric, you can see the slopes are a little bit different. But still, it's an improvement, and you could maybe say the benefit of using the algorithm here is that Astral 3 can't be parallelized, whereas the algorithm we showed here can be. So here, actually, I limited the number. I limited RTIST to just one thread. I guess it doesn't matter on the log-log scale, but anyway, that's what you have. Right, and just to see that it is indeed this bipartition similarity effect that's speeding everything up, here's a graph where you see a ratio of the bipartitions per subset or per cluster in the gene trees, and here is the runtime. So you can see that for Astral, both exact and approximate, as the number of bipartitions per subset is increased, the runtimes, excuse me, what what am I saying? Well, you see the runtime is increased for Astral, whereas when the number of bipartitions per subset gets very large, and this is usually corresponding to more gene trees, there's kind of this no change, right? And so you can interpret this as the saturation effect indeed really speeding everything up or slowing everything down, depending on which side you're looking at. Right. Also, the way that this is constructed, it reduces your memory usage. So when you're using this top-down approach that Astral is using, okay, I just realized this is kind of sounding like I'm saying bad things about Astral. It's a phenomenal piece of code, and it actually works very well. and it's the only one that would work for many, many taxa. So it's kind of the gold standard, maybe just to defend it a little bit. But anyway, when you're working with many gene trees, a top-down approach is going to require you to have this very large stack where you're, in your memory, where you're keeping track of, your calculations over many gene trees, over many bipartitions, and so on and so forth. And that's going to happen for both the approximate and the exact case. And it's going to be linear in the number of gene trees. So as your number of gene trees increases, your memory usage is going to increase very fast. And well, not very fast, but it's going to keep increasing. That effect is not quite as visible in RTIST because you've pre-computed everything. So you don't really have to create this gigantic stack that's, recording a million numbers. And so you see the memory usage here. And this is actually why we couldn't run the simulations. We couldn't run any simulations with Astral reliably past roughly the 500,000 gene tree number, because sometimes it would time out and sometimes it would, run out of memory, and it would crash in the cluster, and we had some issues with dealing with that. Right. So that's the memory usage, and then finally, it gives you this cute feature, which was one of the features we were looking for in our original project. And instead, you can look at suboptimal trees now very easily. So you pre-compute the weight. Pre-computing the weights allows finding suboptimal trees. Just for fun, we looked on an empirical example with a gibbon data set, which didn't have 500,000 gene trees. It had 12,000, which is a lot less. But it still allowed you to explore and see what happens with, allows you to see what happens when you have, for instance, fewer gene trees, or how confident you are of your median tree. So for instance, over here, we first looked at all the gene trees. We looked at the median triplet tree and the median quartet tree, and we found that this was the, we found that there was an optimal tree and it coincided. So here in this histogram, there was two, but if you look at a better one, it actually looks like this. So the maximizer was the same one. We were curious about how good triplets are versus quartets when you have fewer gene trees and effects like that. And when you don't have many gene trees, you start seeing that a bit more. So for instance, here you have the median quartet tree here and the median triplet tree here. And this is the normalized triplet score. So there is no reason to think this one's better than this one, right? It's just how it's ordered here. So we want to analytically figure out the effects of choosing one distance over the other, especially as the number of gene trees is increased. But this is a nice feature. And to be honest, I'm not fully sure how useful it is, but it was fun to play around with. Right. And so in conclusion, the current implementation is for exact calculations, but can be extended to approximate solutions. And if you see how Astral and Stellar do it, is they basically look at all the bipartitions that exist in your gene trees, then they chop them in half. They treat each one as a cluster, and then they look at every possible combination of one cluster and another that are disjoint, and they try to reconstruct the gene tree from that. I wanted to do this when I was writing this, but I thought, okay, it's really not necessary. But when I found out that Astral 3 is using this polytree structure, I realized that perhaps I could try it as well. And so basically, if you can come up with how to write the kernel in terms of the clusters that you have from your gene trees, then you could re-implement this algorithm and see what happens. Empirically, the number of calculations that you do exactly for 18 18 taxa is very close to the number of calculations you do in the approximate case in Astro 3 with any empirical data set with like hundreds of taxa. So I think there's some potential there. Some benefits is that it's completely parallelizable. So you can compute weights in parallel or in different nodes. And if you'd like to check it out, it's available online. It's in, well, there's a big one here. It's also in Python. It's written in Python, but the weight calculation is done in C and OpenMP and kind of stuck together with Python in a fairly amateur way, but it works for now. And one thing that I didn't mention is that the picture is done as rosy when you have missing data. If you have missing data, then you can expect, it can handle missing data, but when you do it, the saturation of the bipartitions to clusters ratio happens much later. And the same thing happens with estimated gene trees. So we're running some simulations right now to see what the effects are, but we've not quite, those simulations take a long time. And so I can't give you a definitive answer on what happens other than things get worse. So maybe I'll tell you next time. And if you'd like to see a preprint, it's available. We have a few kind of stylistic revisions left, but it's been accepted with minor revisions. And thank you very much for your time, and apologies for not taking 60 minutes of your time, but actually something like 120 by missing the first talk. And here are some references that were throughout the talk. And that's it. Thank you.